Alright guys, we're switching into the LearnAP Chem live stream now, so if you have any questions about AP chemistry, be sure to ask away and I will answer your questions. Similarly, we have live streams for Calc that just ended. Those run from 4 to 5 p.m. Eastern. Okay. So if anybody has any questions, feel free to ask away. To start, I'm going to get a copy of the periodic table. If you guys didn't know, we do new chem videos every every Monday and Tuesday, Monday and Wednesday. So be sure to subscribe for that. And if you guys have any questions, feel free to ask away. Alright, seeing as there are no questions right now, I'll talk a little bit about the periodic table a little more. So you might be a little confused by this. Before I'm sort of getting ahead of myself. So what we have here is that on this table, we can see that a lot of our gases are in the same groups, our liquids are in the same groups, solids in the same groups, etc. So properties going down the table like so, elements going down the table like so have similar properties, and that's for a very specific reason, is that they have the same number of valence electrons. So I'll write that down really quick. Groups share similar properties because they have the same number of valence electrons. So we can see here that as we go down the group, we're going to have the same number of valence electrons, and that leads to similar properties. So first here we have these noble gases. You don't have to memorize the names of these, but I mean you can. It's sort of useful. And if you guys know anything about these are all extremely stable because they have full shells. Their valence electrons are always full. So like helium, neon, argon, krypton, xenon, radon, these don't react with anything because they don't have valence electrons. That being said, if we go over here to hydrogen, lithium, sodium, potassium, rubidium, caesium, and francium, these are called the alkaline metals. Except for hydrogen. Hydrogen's weird, but it does share similar properties because it has the same number of valence electrons. These are all really unstable, so hydrogen gas is explosive. If you ever drop lithium or sodium in water, that explodes as well. So all these things are sharing similar properties because they're in the same group. And I could go on and on, you know, the alkaline earth metals also are very explosive because they have 2 valence electrons, and these are a little more because they only have 1. But you guys sort of get the point. Again, if you have any questions, do ask away. I'll be answering questions for the full hour, so from 5 to 6. I can start here One topic that I thought might be a little confusing in the videos was subshells. I'm sorry, okay. So subshells, and I talked about how to write out subshells and electron configurations using the periodic table. Okay, so I see your first question. You have to memorize periodic table for the AP exam. God no, do not do that. You get an equation sheet on the AP test, and that'll include the periodic table. One thing to note, however, is that I do not think that the equation sheet you're given includes the names. So, do note that. So you should obviously know that, like, fluorine is F and so on and so forth. But you certainly don't need to memorize, like, pentium. Just, be familiar with it, and you'll get more familiar as you do more. So another question, what things do you think we need to memorize? Good question. I'm going to be posting a video coming up this Monday about that, but since you're on the live stream, I figure I'll show you. I'm sorry, not this Monday. It's going to be a week from Monday, but I will show you the things that I think you should memorize. So first thing is these metric conversions. So you got to memorize the multiplication factors, the symbols here, and the prefix. So know that a gigameter could also be written as like this, and then it would equal, so we'll say 1 gigameter equals 1,000,000 meters. You should also know that 1 liter equals 1 centimeter cubed, and that the density of water is 1 gram per liter. You should also know these pressure conversions. Right now you probably won't be working with pressure, so maybe you want to put this one off. But eventually you're going to want to know that an ATM equals 760 millimeters of mercury, 760 torr, or 101.325 kilopascals. And do note that that'll be given on the AP test. However, I think it's certainly important in terms of speed to know that rather than having to constantly flip through your equation sheet. And when you do work with pressure, you'll be sort of using these pretty often, so it shouldn't be too hard to memorize. Alright, and then finally, here are the polyatomic ions I think you should know. So we have these positive ions and our negative ions here. Note that a lot of these things are sort of, in terms of our negative ions, our negative groups like sulfate and sulfite are going to have the same charge. So if you saw SO3 but you knew SO4 was -2, you can certainly say that SO3 is -2 as well. Similarly with like chlorate, hypochlorite, wherever that is right there. So maybe you want to take a screenshot of this. The live stream will be available for replay once we're done, so you can just fast forward if you'd like, but I'll give you a second to maybe take a picture if you'd like for this. Okay, if I do continue watching your videos, will I get all the content, or is this just a review? Good question. So this is basically, we're going to be comprehensive. We're going to cover everything. However, we're not going to be spending a ton of time on certain topics and working at the nitty-gritty. So what this would be is it's an overview of everything, but we're keeping it short. So, you're not going to be spending hours upon hours watching our videos. So this would be good for a quick refresh, but also, if you're looking to self-study or something, you could certainly use our videos, and definitely ask in the comments if you have any questions, because we do sort of fly through things that might be fast for some people. But good question. And then, okay, so yeah, that's sort of everything I recommend that you know. Solubility rules, I'm pretty sure that those will be given to you. I might have to check on that, but I would not memorize those right off the bat for sure. Alright, so if you guys have any more questions, feel free to ask away. And I was just talking about subshells. So, building off your question, Arnold, certainly if something you feel isn't being covered enough in our videos, you can definitely ask in our live streams. Do note that we'll have all the videos up by November, so you're not going to have to be staying up the night before the AP test to watch our final video. And if you're looking for extra resources to help you learn, we have a video on that as well on our channel, so be sure to check that out if you're interested. Alright, so I was talking about electron. Our teacher, okay, maybe you do. When I first took the AP test, I did not, so maybe that's changed from 2 years ago. If your teacher tells you you need to, then I would defer to your teacher and memorize them. The College Board should have a resource on their website. I can put that up after the video for solubility rules. Anyway, if you have any other comments, I'm going to get started on electron configurations. Feel free to ask while I'm talking. So, I talked about using the periodic table for solubility rules and scratching out helium and putting it over here. And that's because, just to note on the periodic table, is that helium and hydrogen are sort of weird. You know, helium has 2 valence electrons, but it's not drawn over here. And that's because those 2 valence electrons are first subshells. So the shell is full. So when I say 2 valence electrons for helium, the shell is still full, unlike 2 valence electrons for beryllium, where it's 8. We have 2 valence electrons, but it can store up to 8. For helium, 2 valence electrons, but it can store only 2. Okay, so we see here that you do not, in fact, have to memorize them. So yeah, should understand them. I'll talk more about solubility in future videos, and I'll certainly give you a guideline as to understanding them better, but yes, you do not have to memorize solubility rules. Thanks for that comment, Richard. Okay, so as I said, helium can be a little strange because we have 2 valence electrons, but we put it here because it's subshells full. So I talked about using the periodic table for writing out our subshells. So here we have S. Here we have P. Here's D. And here is F. So, let's say I wanted to write out the electron configuration for phosphorus. Now what we want to do to find this is we're going to start at the top left, snake our way across until there's nothing in that group, and then jump down a row on the left and continue to do the same thing. And we're going to keep doing that until we hit our element here, phosphorus. So here we start from the top left and we go across. And what the period is going to say is our energy level, and the group is going to tell us the shape, and the amount of things we get to is going to tell us the amount of electrons. So here we're in the first period in the S shape, and we're jumping across 2 atoms, so we are going to have 2 in that subshell. Now, if we keep going across, we can see that I'm not going to get anywhere, so we can move on. We jump back down here, and we go all the way across. So here we have lithium and beryllium. These are both in S, and the second energy level. And we have 2 of them. Now, as we go across, we can see that we get into the P group, and we have 6. So again, 2P, and then 6. And then here, we're not getting anywhere. We finish, and so we jump back down here, 3S2. And then we can see that once we jump across these 3 S's, we're not going to get all the way out. We're stopping at phosphorus. So I simply want to include my energy level, 3, my orbital shape, P, and then 1, 2, 3, 3. And that's how we would do that. So if you guys have any other questions or things you want me to go over, be sure to ask. Okay, so we can move on to something similar to this, electron box diagrams. Okay, so we'll say draw the electron box diagram for phosphorus. Do you mind going over the Heisenberg uncertainty principle? Okay, so right now I will go over that and then we'll jump back in. So good question. So let me jump to my notes on that, which I believe was in the first video. Yes. Okay. Alright, I will draw a circle here for the Bohr model. Okay. Okay, so the Heisenberg uncertainty principle is saying that the exact position of particles in an atom can't be determined precisely. So here, when I draw the Bohr model of hydrogen, I say that we have 1 proton in the nucleus. That's excluded from this Heisenberg uncertainty principle. This would not be hydrogen if it didn't have a proton for its nucleus. That being said, I draw this electron on the first subshell. Not on the first subshell, the first energy level. This is just a probabilistic drawing. And we're drawing it in what's called the ground state, meaning that the electrons are occupying the lowest energy level. When it comes to real chemistry, these electrons can be anywhere. They could be, so here we only have 1, so this could be on the 4th energy level, it could be way out in space. Now, the Heisenberg uncertainty principle just says that you can't determine it precisely. What it does talk about is probability. It says that, that electron is probably on the 1st energy level. It's probably not on the moon or space. But you can't determine the position precisely. And so this is where things like quantum mechanics come from, or like Schrodinger's cat, where the cat is both dead and alive until you check the box. Sort of a similar thing. So that's the Heisenberg uncertainty principle. We can probably tell you that the electron is here, but in real life, you can't determine the precise position of that electron. So good question. Okay. So let's draw the electron box diagram for phosphorus. Unless somebody has more questions. Again, this is not supposed to be me just spouting off whatever I want to talk about. This is your live stream. So if you have questions, ask away. If you don't, that's fine. I'll continue to talk. Okay, so we have another question. Is there a chemical reason? Okay, I see what you're saying. So what you're wondering is that, is it because we don't have the technology to know where the electron is, or is this just a property of physics? And that answer is it's physics. It's not that we don't have the tools to sort of determine where an electron would be, but that you can't determine where it would be because of the laws of physics. And in this territory, we're getting into really complicated quantum theory and cutting-edge theory that physicists and chemists are talking about today. Definitely don't need to know that for the AP test. I think we'd all be sort of screwed if you did, but just know that you can't determine the position of an electron in an atom because of the Heisenberg uncertainty principle. And if you're thinking about whether it's sort of like a chemical question or a measurement question, it is a merely chemical question. That this is a law of physics, not that we don't have a small enough microscope or something. So, good question. Just think about it as it being like a law of physics, like gravity or Newton's first law. But good question. Okay, so again, we'll jump back to this electron box diagram. So if we look at our orbital diagram, electron configuration up here, we can see that we have different s orbitals and different p orbitals. But in the s's, we only have 2 electrons, but in the p's, we can hold up to 6. Richard, no problem. Glad I could help. And that's just because our p orbitals have 3 at each energy level, where s's only have 1. So one actual s orbital, which is a circle, can only hold 2 electrons. And the same thing goes with a p or a d. But there's just more p's. There's 3 of them per energy level, while in s there's only 1 per energy level. And of course, that goes without saying that there's only p orbitals above the 2nd energy level and d orbitals above the 3rd energy level. Or not above, at and above the 3rd energy level. And so that's how I get sort of more electrons in these p orbitals than the s. So that brings me to the electron box diagrams. So all we have to do is write our 1s, and for s's we only have 2. And I'm just going to write these out until I get to the end. So again, for p we have 3, 2p, 3s, and 3p. And so now that I have that drawn out, again, p's always have 3 orbitals per energy level. A d is going to have 5, and f is going to have 7. So here, now all I have to do is draw my electrons. So 1s, here we have 2, so I'm going to draw 2 arrows. Now these are all full, so I can draw these up just like so. However, 3p is not full, so I'm going to stop for a second. I have 3 electrons here, so I should be drawing 3 arrows. And there is only one correct way to do this, and that would be like so. I suppose you could have these going in different directions, but this is the only correct way to do this, and this is because of Hund's rule, or Hund's bus. So I talked about this in the second video, and Hund's bus says that, or Hund's rule, I like to call it Hund's bus, and that's because, you know, imagine you're on a bus, and when people sit down on the bus, they're going to take up the empty seats before they start to sit next to each other. So same thing for energy levels. Or I'm sorry, for electrons and energy levels. They're going to go to the empty ones before they fill up other ones. So as I draw on these 3, I fill up empty ones before I go to one that already has an electron. And so here I don't have to double up. I see that I have another question. Do you have any AP chemistry level questions over quantum numbers? I am sure that I could get some of those for you. So let me go down here and then just give me 1 second while I find some. Okay, here's one. So I have an electron, okay, question. An electron with the 4 quantum numbers 3, 2, -1, -1/2 may be an electron in an unfilled sublevel of, and then we have the option calcium, iron, aluminum, and silver. So here we're going to want to try to figure out, well, what are these quantum numbers meaning and how are they useful to answering this question? So I can tell you sort of right off the bat that this one isn't going to be very useful. Everything is either +1/2 or -1/2. So for right now, we can just ignore that. Firstly, we have our first quantum number, which is our energy level. So here we have n equals 3. Now, before I get going, actually, I'm going to quick write out these electron configurations for our atom. So calcium, write out the shorthand, AR 4s2. Iron is Ar. Ar 4s2 4d6. And then aluminum, if I can find it. Okay, here it is. Neon, and then, okay. Three S2, 3P1. And then silver is krypton 5d9. Okay. Okay, so here I want to be looking at, well, which of these has n equals 3 for an unfilled sublevel? So if I look at the unfilled sublevels, calcium would be 4p is our I will change color just to make this a little more clear. So our unfilled sublevels, here is 4p, here is 4d, this is 3p, and this one is 5d. Now here, the only one with n equals 3 in our unfilled sublevel is aluminum right here. So that would be our answer. Let's see. 3d6. Oh, I'm sorry. Good call. 3d6 for iron. You're right. I was going to say that looked wrong. Okay. Thank you for pointing that out. So, 3D. I can eliminate these two because they don't have n equals 3. So now we'll jump to our second quantum number, 2. Now, 2 is saying that what shape is any not? Okay. Gotcha. Thank you. So so our second quantum number is talking about our shape. So if you guys remember, and this is denoted, I'm sorry, let me just, okay, so this is denoted as m sub l. Got it. Okay, so m sub l. And this is our shape. So this is the second quantum number. So m sub l here equals 2. And remember that if m sub l equals 0, this is s. If m sub l equals 1, this is p. M sub l equals 2d. M sub l equals 3, this is f. And so on and so forth. So we see that m sub l here equals 2, which means we're looking for an open D subshell. In C, it's an open P subshell. So we know that can't be right. And we're only left with this one, iron. So thank you for pointing that out, because I would have written down the wrong answer. But I can check, and in fact that this is B. So really the two main important quantum numbers here when you're doing a question like that is the energy level and the shape of the electron. As you can see that I never used the spin quantum number or the other one. Okay. So good question. if you guys have anything else, be sure to let me know. And this was, I'm sorry, this is L, not M sub L. So this one right here is M sub L, and this is M sub S. So when you're doing a question like this, so our quantum numbers are as follows. It's going to be N, comma L, comma M sub L, comma M sub S. So, you know, when you see 3, 2, minus 1, minus 1/2, you should immediately think of this. And then start with the energy level, start with the shape. What is L equals 4? You can go beyond F. I believe it starts at G. Let me just quick check. Orbital subshell shapes. You wouldn't really go beyond F, but beyond that for L, as you increase, you just keep going up the alphabet. So I believe the next one is then, so like L equals 4 would be G, although I'm not 100% on that. You wouldn't need to know that for the AP Chem test, but it's a good question nonetheless. Okay, yeah, so this is G, and then L equals 5 is H, and then you would just keep going up the alphabet. But good question. Okay, so I'll write this out as L, so we say L equals 6. I'm just going to do the next letter after H, which would be I. I would highly doubt that you would see L equals 4, but I would be very surprised if you saw L equals 5 or 6. That I would be very surprised. Okay, so let's move on to something else. No problem. Okay, we have another question. Why are cations larger than anions? So, write this out. Cations have a larger atomic radius than an anion with the same number of electrons. So that cations are larger than anions is sort of a quick way of saying cations have a larger atomic radius than an anion with the same number of electrons. So let's talk about why that is. If we remember, I will change color here real quick. Okay, so if we remember, cations have a positive charge and anions, get my red, anions have a negative charge. So if we think about this, let's say we have a cation with 2 electrons. So I'll just draw some random cation that you would never see with 2 electrons. Sorry. Or no, you would see this. So this would be Li plus. So here's a cation. Similarly, I'll draw an anion that you might see. I'm sorry, this would be... Okay, no, I'm sorry, I just confused myself for a second. So, similarly, I'll draw out an anion with 3 electrons. I'm sorry, with 2 electrons. So, this here would be H minus, and this... Okay, wait, that was right. Cation, anion. So, going back to our statement, cations, like here, have a larger atomic radius. I'm sorry, this should be smaller. Have a smaller atomic radius than an anion with the same number of electrons. So if you think about it, here in our cation, these electrons are being pulled in by a stronger force than here. And so these electrons are going to be closer and closer to our nucleus. However, an anion, these aren't going to be pulled in nearly as close because we have fewer protons, and thus they're going to spread out larger. And so that's why a cation is smaller than an anion. So do note that a cation is smaller than an anion. And in case you're confused, atomic radius, simply talking about how far are these electrons in terms of their orbital's radius. So here, this right here, if this were a perfect circle, would be our atomic radius. So good question. Oh, don't worry about it. I should have caught that earlier. Simple mistake to make. Okay. If you guys have any more questions, feel free to ask away. Maybe you want me to do a problem on some topic that's confusing you, I can certainly do that as well. Okay. We don't have any more questions. So yes, anions are larger than cations. Yes. So for the reasons I just talked about, an anion is not going to be pulled as close to the nucleus as a cation would, because this cation is positive, that's pulling the electrons closer, while this anion is negative, and they're still being pulled in, but not as much of a force. So it's important to note that when we talk about something like this in terms of attraction being shielded, these electrons are all feeling the same force of the nucleus. However, the electron shielding you might have been heard happens from these electrons of the same charge repelling each other. So that's what sort of keeps these electrons from just melding with the nucleus, is that they're repelling each other, and that's pushing them away. So certainly something to note there. And so that's sort of another way to think about Hund's rule, is that an electron is not going to fill up orbitals unless all available subshells have been already... I'm sorry, let me restate that. An electron is not going to join an already occupied subshell unless all other available subshells already have an electron, because it's not going to want to join that and repel the 2 electrons. It's going to want to join its own. Having 3 other AP classes doesn't help. I feel you, but certainly AP Chem, if you put in the work, do some practice problems, it should not be too hard to get at least a 4 or a 5 on this test, but I certainly feel you in terms of having trouble. I took, I think, 4 at the same time as well, so I feel you on that. Live streams might, yeah, exactly, that's what we're here for. We're here to sort of help you guys on the AP test, so whether that's leaving a comment if something's confusing you, or joining us here on the live streams or watching our videos, that's basically what we're trying to do. So hopefully we can sort of help you do better on AP Chemistry. Alright, so I didn't do a practice problem with wavelength and frequency, so I can do that real quick right now. Okay, so I told you that lambda, or wavelength, wavelength times v equals c. So c here is the speed of light. V is frequency. And lambda is wavelength. In my high school, the highest score ever was a 4. I'm sure you can pull off a 5. Just, keep coming to the live streams. I'll be doing this every day, 5 to 6. So be sure to come in, ask us questions, and hopefully we can sort of help you get another 4 or even break the record. So there's that. Anyway, talking about wavelength and frequency, I didn't get a practice problem when I did this in the video, so I'll talk over this a little more. So let's say I have a wavelength of 400 nanometers in C. Sometimes you'll see it as 3.0 times 10 to the 8th meters per second, but I mean, I would just write it as 2.998 times 10 to the 8th meters per second. So, that being said, we can solve this. Now, note that when we work with these, I actually need to have this in meters. So, if I convert this real quick, I would have this as 400 times 10 to the negative 9th meters. I guess that's not proper scientific notation, but if you're plugging this into your calculator, I wouldn't really worry about it. That being said, if you're on the AP test, you should probably just, if you're going to write this on the test, you should write it as 4.00 times 10 to the 1/2 negative 7th meters. Okay. So, now all I have to do is what's called plug and chug, and this is sort of a theme of AP Chemistry, is you just know the formulas, you know the principles, you have the numbers, and you plug it in and chug. So that's why it's called plug and chug. And so here I'm just solving for V, and here I would get 7.5 times 10 to the 14th. Now again, you might be wondering, well, what's my unit? Do I have to sort of involve meters per second and meters and try to figure out what the units are? If you didn't know the units for V in this equation, you would have to do that. But I went over this in my video, and the units for V in lambda V equals C is hertz. So you can just write hertz. You can also write seconds inverse. So I guess this brings me to a good point is, let's say I didn't know that the unit was seconds inverse. How would I find that? So a good thing you could do is simply plug in the units to the equation, but not the actual numbers. So meters times V equals meters per second. Solve for V. So I'm dividing both sides by m. I can cross these out, and I'm left with 1 over s, or s inverse. And s inverse is the same as hertz. So that's certainly a good thing to know how to do. Alright, we're reaching the end of the live stream, so be sure to ask. Will we have... Oh, absolutely. You will, like I said, plug and chug is sort of like a main thing to do on the AP test is, you'll have an equation that like this, or maybe, we'll talk about like solubility constants, where literally all you're doing is you're trying to find the correct numbers to plug into an equation like this. You plug it in and you solve. That being said, certainly there's a lot more to it than that. You should definitely sort of understand the underlying principles behind a lot of this stuff. But in the end, you can get away with a lot if you just simply know the equations and what to plug in. So, good question. But as I was saying, if you guys have any more questions, I think we're in the final 10 minutes. So be sure to ask away, and I'll try to answer as best I can. I'll talk about this again. I talked about the electromagnetic spectrum in the second video. And I have this image here, courtesy of NASA's website. And you might be wondering, well, do I have to memorize, gamma ray, X-ray, UV, visible light? Do I have to memorize, what's the frequency for gamma rays or radio waves? And the answer is no. You don't have to memorize that, with the exception of visible light, which is wavelength is 400 to 700 nanometers. Don't memorize the frequency because, again, lambda V equals C. If you really wanted the frequency, you could just plug that in and solve that. So, but you will have to memorize that gamma rays are sort of on this end of the spectrum, and then X-rays, then UV, visible light, infrared, microwave, radio. So memorize the order, memorize that gamma rays are the highest energy, highest frequency, shortest wavelength, but other than that, you're not going to have to memorize wavelengths or anything, with the exception of visible light. And one more thing, do keep in mind this is in nanometers. I suppose you could write that in meters, but I find it's much easier to memorize the nanometers and just convert it. Is Princeton's Review 2016 book alright, or do I have to purchase a 2018 one? 2016 should be completely fine. The 2018, they do tweak the AP test just a little bit, but if you have the 2016 version, that's going to serve you just fine. Princeton Review is a very good book, so you will probably be just fine having the 2016 one. Good question. In terms of just how the AP test is changing in general, they're not going to, they might introduce new topics or take away old ones. However, what they're mainly doing is shifting their focuses between different subjects, but it's not, they're not changing it a ton. So, the 2016 version should be just fine. What I would do, Arnold, is I would see if your teacher knows how the AP test has been changed since 2016, and that way you can sort of keep that in mind as you're using that version of the Princeton Review. Okay, so we can also talk about some other things now. I guess I can go over the Bohr model a little bit again. I believe this was in video 2. Okay, no, it was in video 1. It's in video 1. Yeah, there it is. So I talked a little bit about how this is wrong for everything except for hydrogen, and that's because the Bohr model is only using S shapes for all of its energy levels. Just a quick side note, Arnold, if you do buy the 2018 one, you can check out our resource recommendation video, which we have on this channel, and we also wrote an article on our website under the resources tab for LearnAP, so you can check out our article there. Just go to learn-ap.com to check that out if you're interested. That being said, 2016 should be fine. Teacher has a PhD in chemistry. Oh, okay. I've had teachers like that. I'm glad that this channel can help you. Certainly tell your friends about it if they're encountering similar difficulties. Okay, so let's see what else we can talk about. I believe we only have like 3 more minutes, so Arnold or Richard, if you guys have any more questions, I think I have time for maybe 1 or 2 more questions. It doesn't have to be like a math problem. You can just ask about AP chemistry in general as well. Just so you know, I took the test 3 years ago. I got a 5 on it, so that's my experience with the AP test, if you guys were wondering. I guess I can also talk about, I did put up a video about calculator policy on the AP test. If you were wondering, just go over sort of policies, allowed calculators, like calculators that I would recommend that you use. Okay, so we have a question from Richard. I have a question about the live streams. Are you going to do more around time of the AP test? And the answer is a resounding yes. I don't know exactly what my schedule is going to look like around then, but I will be trying to live stream at least every day, the week or 2 weeks before the AP test. You know, that's in May, so I'll have more information about that as it comes out, but yes, do know that we'll be live streaming even more come the weeks leading up to the AP test. That being said, if you guys were confused or didn't catch this, we're going to be doing live streams every Sunday from 5 to 6 p.m. Eastern for chemistry. And then we also have 4 to 5 p.m. Eastern for calculus, if you're taking that. So every Sunday, mark your calendar. You can like us on Facebook or follow us on Twitter to view that. The link should be in any one of our videos to find those. You can find us on Facebook, we're at LearnAP, and on Twitter we are at _ LearnAP. So I'll just write this out. Facebook at LearnAP, Twitter at LearnAP. Okay, so we have another question. Does helium have the same properties as group 2 elements? I was talking about this earlier, and the answer is yes. Or I'm sorry, not group 2. The answer is no. It does not. And so here we can say, group 2 is the alkaline earth metals. Whoops. And these have 2 valence electrons. Now, helium also has 2 valence electrons, but there's a very important difference between the alkaline earth metals' 2 valence electrons and helium's. And that's that helium's 2 valence electrons are a full orbital. So if I draw my just Bohr model here real quick for helium, I can see that I have 2 electrons on this first orbital, 2 valence electrons. But if you think about it, if I had to add another electron, it would go on another orbital. And so I'm in what's called a full orbital. And because of that, helium's very stable. It's not really going to react with anything. It's not going to be changing electrons and trying to fill up its orbital. That's what elements want to do. They want to fill up their electron orbitals. So when we talk about hydrogen gaining or losing an electron, it's trying to essentially fill or just lose its electron. So it has a full orbital. So helium already has that. So it's not going to be giving away electrons and reacting with things because it already has a full orbital. That being said, these alkaline earth metals here do not have full outer shells. They have 2 valence electrons, and so they're going to be readily giving those electrons up to other things to try to achieve a full outer orbital. So they're going to react with a lot of stuff. And so the short answer to your question is no, that helium does not. And if this is confusing you, you can just look at the periodic table. These are all sort of organized according to their properties. You know, so that's why helium is here and not here. Similarly, however, you do have here, we have like the halogens on the staircase and the semi-metals here. These share the same properties, but they're a little bit different. But in general, if you're wondering, groups share the same properties on the periodic table. Also valence electrons with the exception of helium and hydrogen. So good question. Alright, so that about does it for our live stream, guys. I want to thank you guys for tuning in. If you found this video helpful, be sure to leave a like and subscribe for future content if you haven't already. If you didn't catch it, we'll be doing live streams every Sunday, 5 to 6 p.m. Eastern for Chem. We also have 4 to 5 p.m. Eastern for Calc every Sunday if you're interested in that as well. Other than that, I want to thank you guys for watching, and we will have our next Chem video up Monday. So I'll see you guys then.